Welcome to a lesson with Dr. Powell. This is part 2 of a lesson that I have right here on a close look at continuity and limits. We've defined some terms. We've defined, and just kind of briefly thinking about it, we've defined image, preimage, codomain, and we've discussed kind of an idea of fuzziness, and kind of come down to this particular idea. A function is continuous if and only if for every y value in the codomain, an epsilon greater than 0, we take some codomain fuzz, and what we need is that, now that's kind of a fun word that we were using in the last part, so please go back and take a look at that so you can understand where we're at and where we're starting. So we take some fuzz in the codomain, and we want to show basically that the preimage of that is fuzzy itself. And we were talking about why that might be good for a good description of what it means for a function to be continuous, even intuitively. So take a look at that first part for that. But we're going to go on to talk about what it means. So that description that we just went over is actually what it means for a function to be continuous on its entire domain. That's what we had from part 1. In part 2, though, we're going to talk about what it means for a function to be continuous at just one point. All right? So, I mean, look at this example. I mean, it's kind of pixelated. I mean, the domain here of this function is not even everything. Like, it just jumps around, right? In the domain, you have, things are changing. In fact, look at this description right here. The domain might look something like this, just kind of points along here. It's not even a whole interval. And the y values similarly. Or even this example here, we have some, the y values are kind of jumping around a lot. And they're heading toward, and just make sure it passes the vertical line test. And as it heads in, these points are getting closer and closer to a point A. We can say in both of these cases, actually, that a function is continuous at x equals A. That's one way of describing it. And so we're going to modify our definition that we have of continuity, so it really satisfies this idea. All right, just to kind of get some precision here on what it actually means. So what we're going to do is we're going to require that the preimage of codomain fuzz at L, but you know what we're going to do? We're going to say L is equal to f of A. All right, because really if it's continuous, that's what we want anyway. We want to choose, we want to be looking at that point. In fact, we're thinking of continuity at one point, so we're really only concerned about what's happening as we head up to that one y value where A is in the domain. So we really can't think about continuity at a point, first of all, unless x equals A, unless x equals A is in the domain of the function. So we can plug it in. We're going to get that. All right, so that's kind of nice. So we have codomain fuzz centered about f of A, going down epsilon and up epsilon. We want the preimage of this guy to be fuzzy, at least as much fuzzy as we can. I mean, wow, this domain is kind of like lots of different points here. But basically, we want it to be, we want the preimage to contain all domain points that are in fuzz. So the domain kind of is embedded in, on the x-axis, and there's fuzzy spots on the x-axis. But basically, what we want is that a fuzzy spot in the domain is actually just points that are inside of a fuzzy spot on the x-axis, kind of like an intersection with the fuzzy spot and the domain. So right here, take a look at this. Like points right here, these points are actually in a fuzzy spot centered at x equals A, going that way and that way. And so we're going to call that fuzz in the domain. All right. So so we're going to require that the preimage of this contains all domain spots which are in some fuzz centered at x equals A. So basically we want x equals A kind of to be contained in some fuzz in the domain that way. Going out a little delta and delta that way. All right, so basically everything in here needs to map up or have an image inside of there, and that's going to be our description of what it means to be continuous. So continuing onward, all right, again with the point that we are going to L being f of a, I'm going to think, okay, given epsilon greater than 0, so namely given some codomain fuzz, we want to show that there's some domain fuzz, all right, some delta greater than 0, some distance there, so that here's our interval on the x-axis, but all the domain points in here, okay, all the domain points in this fuzz, we want them to actually come up and have an image in there, to come up to this fuzz in the codomain. So, so centered at A, we're going delta, delta, we have an x point in that fuzz right here. How can we describe if we're in that in this open interval in this fuzz? Well, basically what we want is we want the distance from x to a to be less than delta. So here, distance between things is subtract absolute value. That's nice because that means you can, you know, put a on the other side or whatever else, and you'll still get a positive distance. We want this distance to be less than delta, in particular if x is equal to a, because a is in the domain. We're going to assume a is in the domain here. That's fine. You'd get 0, and that would be really good. Okay, so absolute value of x minus a is less than delta. We want that, which just says that the x value is in this kind of centered fuzzy spot here in the domain. We want that to imply that we're actually heading up to the codomain fuzzy spot for the image, which this is the way we describe that. That's one way of saying it, because our image, its distance to L, is going to be less than epsilon. All right, so that's kind of one way of writing it down. Okay, so continuity at a point x equals a. We can say this is as the following. Given epsilon greater than 0, there exists a delta greater than 0. These are just a small number and another small number, but we use epsilon and delta just to kind of be thinking about what they're going to be referring to. Epsilon for the codomain fuzz and delta for the domain fuzz distance. There exists delta greater than 0 such that if so x is in this fuzz centered at a, then its image is going to be in the fuzz centered at f of a. Okay, that's continuity at point. That's a kind of a nice definite. Well, maybe you don't think it's a nice definition, but it is a precise one. And so that's not going to have any loopholes and funny things that are going to kind of come about it. And mathematicians need that, or even just people. Sometimes you don't even have to be a mathematician, but understanding this type of thing can be useful for at least for tolerances and knowing kind of how things are changing and bits and that in different settings in a variety of disciplines, not just mathematics. But if we continue onward, we're going to look at an example of this in action right here. Let's take a little simple function, y equals 2x, or f of x equal to 2x. If we think about, take some codomain fuzz, is there some domain fuzz such that if the x value is in the domain fuzz, we're actually outputting in the codomain fuzz? Well, let's look at the worst possible case when we push that domain fuzz right to the edge, right there. Like if it was any further, the x value is right here. Look, y value would be outside of the fuzz. That wouldn't be good for the images. No, we want it to be right here. So we're going to push that out so we can see a nice relationship between a possible delta and epsilon. So you notice here where it says there exists. Well, to illustrate this idea, we just, instead of saying there exists, we actually illustrate what delta is. We write it out, what a good delta would be. In this particular case, maybe in terms of what we have given, right? Like the things we're starting with, like epsilon is one of the things we're starting with. So we can write it in terms of that. For instance, given epsilon greater than 0, I'm going to let delta be epsilon over 2. Why would we do that? Well, this line has a slope of 2, right? And look at this. We're going over delta, and then we're going up epsilon, delta, epsilon, slope of 2. The ratio between these two guys is 2. which means delta is 1/2 of epsilon. That would work. So if delta is equal to epsilon over 2, right, then that's enough to ensure by the picture right here that if the distance from x from 1 is less than that delta, which is epsilon over 2, then the y values will be within epsilon of 2. It'll be in the right codomain fuzz. All right. So that was continuity. But we also can have like continuous on one side, left continuous, like here. We come up here, continuously drawing, we fill in there. That's as much as we go right there, right? So this would be an illustration of left continuous. And we will address this topic as well as right continuity in the next video in part 3. Thanks for watching.